Hello, today we'll be looking into binary search. The focus of this session is understanding the structure of a binary search problem. So here we'll code 3 questions and get a common structure, how the binary search problem will look like, and what are the conditions we write to solve the problem, and what is the code. So the first 3 problems are these. I'll state them. So there are n versions of the code. Let's say v1, v2 up to vn. We have an API saying that is the version bad or not. So the API says that is bad version of vi. It returns a boolean value saying that the version, ith version, is true or false. True implies vi is bad, else vi is good. So given n versions, we want to find the version which is good, the last best version. We want to go there. So let's say we have 1 2 3 4 5 versions, and we are given 5 as input. 5 is the input here. And we need to find which is the best version. Let's say 2 is the one, and we don't know in advance. So how do we do that problem? So this problem can be stated as minimize version. So here version is an integer subject to is bad version of version is true. So here the things might not be very clear. Let me restate the things. So here the question is, there are n versions. Each version can be a good or bad version, and versions are happening day by day. So vn is happening after vn minus 1, vn minus 1 is happening after vn minus 2, and the second version is happening about after the first version, and there is sequential temporal order between them. So if we have a bad version, all the versions coming after will also be bad. So in this kind of setting, what do we want to do is to find the minimum version which is bad, and once we get the answer, we can confidently say that version, let's say the answer here is min version. We can confidently say good version, the latest good version is min version minus 1. So this is the first question. So let's look at second question. Let's say we are given a number x, given a natural number x, and we want to find the square root of x. So if x is 4, we get square root of x to be 2. If x is 1, the square root of x will be 1. But what happens with x? X is 8. We need to return. So in actual case, square root of x will be 2.7 or 8 or something. But what we will be returning is the floor of the answer, which is 2. The actual square root floor of the answer. So this problem can be rewritten as minimize square root subject to square root square is greater than or equal to x. This might not seem very obvious, so let's look into an example. So what here it takes is, it given a number, it looks and finds the largest number whose square root is greater than the existing number. So if we have 8, 1 into 1 is not greater than 8. 2 into 2 is not greater than 8. But we have 5 into 5 greater than 8. So we want to have that 5 as small as possible. So we look into even smaller ones. 4 into 4 is greater than 8. Okay, no problem. We go even further. 3 into 3 is greater than 8. Fine. 2 into 2 is not greater than 8. So what we have the answer here is 3. What we will be returning is the answer. Let's say it is min square root minus 1. So this is our answer. So here what we are doing is, we are finding the smallest number whose square is greater than the existing number and return the number subtracted by 1. So I repeat again. So given a number x, what we are finding is the minimum number whose square is greater than the existing number. So here if we have the number as 8, 3 square is greater than 3 square is greater than 8, and that is the smallest number whose square is greater than 8. And thereby what we return is 3 minus 1 as 2. So this is one problem which is posed as minimize square root subject to square root square is greater than or equal to x. So let's look in another problem. The third problem is the very famous problem. So given an array A, find the position for given target find the position for the given target to be inserted. And the given array is sorted in ascending order. So this is a very famous problem. So how do we, so let me give an example for this before I proceed to how do we pose the problem. So let's have, we have an array 1, 3, 5, 6 and the target is 5. So where do we insert this 5? We insert it in this position. So it is the second index. So the index is 2. This is the return value. So let's have the same array again. And we want to insert 2 here. And the position we will insert is 1. And the resultant array is 1, 2, 3, 5, 6. In the above position it will be 1, 3, 5, 5, 6. So the question I think is very pretty clear. So how do we pose this problem? So what do we pose is we want to find the minimum index. Minimum index, the problem is minimize index subject to a of index is greater than or equal to target. So yeah, we have been discussing, we are looking at these questions. How are these questions related to binary search? So binary search has this peculiar thing saying that we want to, so binary search tries to solve these kind of problems. So minimize some k subject to condition k is true. So let's say we are looking for a condition and we want to find k, the smallest k which satisfies this particular condition. So this is a problem which is this is a specific type of problem where the condition is always true for the upcoming cases if the current state condition is true. So this problem, let's look at this problem, the question 3. This problem can be found out in a iterative fashion by looping it. So but what the primary purpose of binary search is searching in a ordered fashion in log n time. So identifying the binary search problem is in this way. So let's say we have a condition defined and that condition is always true for the upcoming cases but not for the previous cases. So if we have such a condition and we want to find the minimum of that, the first time when the condition is true, that is when you use the binary search. Things may be a little bit unclear, but the more we look into this case, we'll try to understand. So let's look how do we solve this problem. So there are three key steps we need to inculcate when solving this problem. The first step is we need to define the search space. Steps to solve a binary search problem. So now that we know how to identify a binary search problem, we'll look how do we solve it. The first one is identify search space. The second step is what is the condition And what are we returning? So let's go through these 3 steps for these 3 problems. So in the first problem, the search space is from 1 to n. So let's say L is the minimum one, and so the search space can be denoted as L to R. L to R. So smallest one is L is 1, R is n here. And what is the condition we are looking at? The condition here is bad version. So this is our condition we are looking at. So this is our condition, and what are we returning here? Sorry, my bad. So the question is, we want to return the latest good version. So which means we will be returning L minus 1. So L is the last one which satisfies this condition. So L is the last bad version, the first bad version, and the latest good version is L minus 1. So how do we go about writing code for this? So binary search goes this way. The input is an array. L is 1 here, R is n, and so this is kind of a template, we need not change much. So I will just bold things where the things need to be changed. So this is one place where we need to change the code. Okay. So this is, and the next place where we need to change the code is not here but later. Yeah. So once we have found a mid position where we want to separate things out, we will be looking upon a condition. Based on that condition, we'll be making our problem smaller. So here our condition is bad version of version. So we'll look at if is bad version of mid. Then what do we do if it is a bad version? What we do is making the problem smaller from the right side. So right will become the mid. Else we have got a good version, but it is not the latest one. So what we do is we make the problem smaller from the left side by making L is equal to mid plus 1. So in the end, what are we interested in is return L minus 1. So this is our condition we are looking at. So this is where we need to change the code, and this is where, so these three things play a key role in writing a binary search algorithm. The rest of the things don't change, but identifying the search space, looking at what the condition is, and what are the written value we were looking at. So these are the key things we decide in a binary search problem. After we identify it, a problem can be solved using a binary search. So let's look at the second problem. So here the second problem is finding the square root of a given number. If the given number square root is in a fractional one, we look at the floor of the answer. So the first thing is we have identified this as a binary search problem by writing it into a optimization problem as such, and we have a sequential fashion, like we are looking at smallest smallest number which is greater than the given number. So if the given number is 8, the smallest number whose square is greater than that number is the one we want, and eventually we will be returning the answer minus 1. So the return value is min square root minus 1. So we can just use the three conditions. So what is our search space here? So the second problem, the search space is L is equal to 0, R is equal to X. Because we want to find the square root of X can go up to X. So we'll be looking at 0 to X. Okay, so what is the condition? So the condition is just this. So this is our condition. So what is our written value? Our written value is L minus 1. So here I am stating it again that L, that most of the time we will be returning, in majority of the cases we will be returning L or L minus 1. One thing which is key thing we need to remember is L will be the last point where the condition is satisfied. So if we look at the L in solving this problem is the first bad version. If we look at in a sequence, here the first number whose square is greater than X. Okay, so L, so the key thing, I'll just make a note here. L is the first the first position / number where the condition, given condition is satisfied. Okay, so let me restate this thing again. So in this problem, we get after processing we get L, which will be the first bad version. In this case, we'll be getting the number whose square is greater than X. The first number whose square is greater than X. So, okay, what do we want to return is L minus 1. So that we get the floor of it. If we return L, it will be the ceiling of the answer. So we can just write the code for this problem just by copying this. Let's copy this. And what is the left? It is 0. What is right? It is x. And here we are given square root x as input. Array is not required. And the question is finding the square root. And the second thing we need to identify is mid into mid is greater than or equal to x. And the last thing is L minus 1. So this is the code of the question. So it's pretty simple, right? But the key things is how we write the condition and how we identify the search space and what is the returning value. So this is the code for the second problem. What is code for the third problem? Let's look at it. Here we are returning index, not index minus 1, the min index. So the third question is given a sorted array in a ascending order. We need to find the position where the target needs to be inserted. Okay. So here we have the condition as a of index is greater than or equal to target. So this is our condition. So what is our search space? Search space is, what are we returning? We are returning the index. What are the possible values of the index? It can be 0 till n minus 1. But what happens if the given target is greater than all the values? Then it needs to be inserted in the last position. So what we consider here is L is equal to 0, R is equal to length of A, length of the array A. So I'm restating again. If you want to insert in the last position, that is when all the elements are smaller than the given target number. That is when. So that's then is that in that case we'll be inserting at the end, which is the last position, which is length of the array. So the search space starts from 0 till the length of the array. And what are we returning? We are returning L. So let's write the code for this problem. Let's copy the code again. So the input here is array and the target. And the problem here is insert, and the index starts from 0 and goes till length of array A. This is the first thing. The second thing we do is looking at the condition. The condition is A of index is greater than or equal to mid. So here is something I think I'm missing. What am I missing? Yeah. So array of mid is greater than target. Sorry. Array of mid because mid is something which is in the search space. So we are searching in some positions. So mid is in the search space. Yeah. And we'll be comparing it with the target. And what other thing we will be returning is L. So this is about binary search. the key things, this is the first session about binary search. We'll have 2 more sessions on the binary search. The first session goes like this. The first thing is identifying the problem, whether it can be solved using binary search, which is we have a sequential fashion and a condition which is satisfied thereafter if the first condition is met. Let's say at the fourth instance we have a condition met, and it is given that, let's say on the fourth condition the condition is met, and fifth, sixth, the following search space, the following states in the search space are obeyed as well, which means the conditions are met in the following states as well. In such cases, if we want to find the minimum state where the condition is satisfied, that's when we use binary search to solve the problems. So once we have identified that it is a binary search problem, and we have well posed problems saying that we have minimized case such that the condition K is true, what do? Is we do the 3 key steps to solve a binary search problem. The first thing is identifying the search space. The second thing is identifying the condition. And the last thing is, what is the written value? The written value is depending on the problem we are solving, but the key thing to understand is L is the first position where the condition is satisfied. So we have solved these 3 problems and we have written code for it. In the future sessions, we'll look at even complicated problems which might seem ambiguous, not very clear. Now, you might try various approaches, but thing might not strike at first that it's a binary search problem. Such kind of problems are the things we'll look at, and 2 more sessions, 4 problems each. That's the plan. So 8 problems to be solved further, and 2 sessions to follow. Thanks.